In this chapter, we're going to look at the other non-parametric tests. And if we were to go back and look at this table about choosing a statistical test, what we're talking about is the tests that go down the middle column. This has to, not with the binomial data on the right-hand side, not with the interval data on the left-hand side, but with ranked data. And there are some other reasons why we'd be using those. So this is for ranked data, or what we also call ordinal data, and then you can compare that to the different ways that we're going to conduct a test. The reasons why we use that, as we said, really small samples. For the people that take applied research, if you're going to have to run some kind of statistics, that tends to become very relevant because this is for small groups. It is for outliers. It's for if you look at the normal distribution, it's for the ones out on the tail that aren't like everybody else. Inferential statistics, what we've done up to this point, has to do with normal groups, normal distributions. We can also look at non-normal distributions or strong non-normality. As an example, the first one, the Mann-Whitney test, is used to compare two sets of data. So for example, if we had males and females and they had completed a survey, that would be comparing two groups on ordinal data. That's just like the independent sample t-test. It's just now we're talking about a different kind of data. But there's other ways to look at that. One of the examples is tennis players. And as we get close to the Olympics, one of the theories in the Olympics is if you're going to be successful at that you have to start before you're 12 years old. This is the same sort of question in that we want to know if early training for tennis players might have something to do with their higher rankings. So we have a dichotomous question, whether or not you had intensive early rank training, and then we have the rank at which the person was currently standing. And we want to know if this on this side has anything to do with this rank. When people first see this, they say, well, that's a correlation that has to do with two things. Well, it can't be a correlation if this is only dichotomous data over here. So for the argument of this, let's say a miracle occurs and we end up with a data set. The data set looking something like this. And this is somewhat like what you will see, and I'm going to show you another example of what it looks like in text. But basically what we're looking for is whether or not there's a change in the ranking, or the ranking has anything to do with early training. So we can see the data is 1 is a yes, they had early training, or 2 is a no, they didn't. How many of each of those there were? Their average rank, ranked 1 through 10 or 1 through 9, it's 1 through 10. And the sum of those ranks. So we took those who were ranked a no, and we added up their ranks, whether it was rank number 2, 7, 8, 9, etc. And they did the same thing with those who did not receive early training. As I said, a miracle occurs, and it kicks out a number. Again, what we want to see is whether or not this value is less than 0.05. So we can see on this, it's not less than 0.05, so we'd say that early training has nothing to do, in this case, with tennis ranking. Now, another example of that, because most people don't write it like that, if you go to page 705 in this document about non-fatal overdoses, the researchers in this study were using, among other things, a survey about methadone maintenance treatment. Well, they wanted to know whether or not what they were doing had anything to do with which drugs the heroin users were involved in. Basically, what I want you to see from this is when you're trying to find Mann-Whitney U scores, or if you see this U like this, that's what that means. That is a Mann-Whitney U test. So there, on this one, it says this greater dependency. MMT subjects had fewer mean drug types in the previous 6 months than did NMM. And here's we can see they used a U-test, and there's a significant difference. So that's what a Mann-Whitney U looks like. If the ranks are not already applied, if they didn't see that, then the researchers are taking interval or ratio data and converting it to ranks, or the computer will do it for them. So that's one example. The other one is the Likert scales, the survey data. You seldom see people using the Mann-Whitney test, the Kruskal-Wallis, or the Wilcox, and the other ones we're going to talk about with this type of ordinal data. And I think it's because people have done it wrong so much that we assume now that it's correct. What you'll see a lot of with that survey data is people still doing t-test or ANOVAs when they really ought to be doing this. Now let's have another hypothetical situation. What if we had more than two groups, actually is what this should say. If we had three groups or more. If it was interval ratio data, if we have three groups, then we do an ANOVA. So let's look at this example. Let's say we had a survey about confidence in math. We had boys and girls taking the survey who also happen to be 6th, 7th, and 8th graders. We have 32 questions. They give us 4 descriptors about confidence in math, how useful math is, whether or not math is a male domain, and teacher attitude. What we want to know is, can we make comparisons using a Mann-Whitney? Again, that has to do with two groups, so we can compare the males to the females. But we also might want to look at just the 6th, 7th, and 8th graders. Is there a difference between 6th and 7th, 7th and 8th, and 6th and 8th? If we're going to do that, we would use something called a Kruskal-Wallis, which you've read about in your book. But again, with a Kruskal-Wallis, we might determine that there is a difference between 6th, 7th, and 8th graders. We can narrow down and just filter out just the male 6th, 7th, and 8th graders. But what we cannot figure out is whether or not there's a difference, or where the difference is in 6th, 7th, and 8th grade. It won't tell us that. Just like an ANOVA won't tell us where the difference is, we have to run a post hoc test. And again, what do we do about that? In this situation, we run a post hoc test. The last one that we're going to look at is something called the Wilcoxon test. Just like we had a dependent samples t-test, we have a Wilcoxon signed ranks test. This is where we have one group that's been measured twice. The reason we're not using the dependent sample t-test is because now we're talking about ranked data. It's ordinal data. If we have multiple treatments, for example, if we do first, middle, and post-treatment, then we can use a repeated measures test, just like we do with parametric analysis. So what happens? Well, each participant gets a score, or is ranked, or completes a survey the first time. And then they are ranked again the second time. What we want to know is this. Is there a significant change in their position after a period of treatment? Not their position relative to one another, their position relative to themselves. Did you change individually, and did every person change individually? So as an example, we have 6 industrial workers who are chosen for a study to determine the effects of rest periods on production. So we go for 1 week and we measure their production. And then we institute a new rest period. And again, we measure their production after that. So we measure their production before. So here's worker 1. He has the most production. Here's worker 2. He has the least production, etc., etc. That's without rest. So we implement the rest period. And we want to know, does their ranking change? So we look at this, and really what we're looking for, you can see how many of them went through a negative ranking, how many have a positive change in their ranking. We can determine based upon this asymptotic significance that having a rest period does make a significant difference in their change. But the question is it a positive or a negative change? Well, to determine that, we'd have to go back and look at, did they go up or did they go down? Well, this one went up, that one went up, they all went up. They changed their order, but they all went up. So obviously it makes a significant change in that. Incidentally, there's something that you probably ought to read about called the Hawthorne studies, and that's relevant to this because the Hawthorne studies had to do with measuring production like this. And what they did was they wanted to determine whether or not changing the conditions of a work situation would have an effect on how productive people are. And what ended up happening is, for example, they changed how much lighting people had while they were working. And they would make the room darker and darker. And what they noticed is the darker they made the room, the more productive the people became. And after studying that for a while, and this is at the Hawthorne Light Company in Ohio back in the 1920s, what they discovered was it wasn't that they were changing the lights that caused a change in productivity. It was because they were a part of a study that when they turned the lights down, the people who were doing the work knew they were being watched, and they didn't want to do a bad job, so they started working harder so that they didn't think anybody's thinking poorly of them. So it ended up having a different effect, and they also started studying people's behaviors a whole lot more. So it went from a study about productivity in terms of simple things like lights to understanding better what happens when we study people, and that the impact of being a part of something and knowing you're a part of something, and whether or not that has an impact on the outcome of the study. So that's it for the videos. There will be an assignment posted for these two chapters, and email if you have questions.